continue our discussion of ideal gas with review problems for specific heat, enthalpy, and entropy. So, first problem, a gas initially at 15 psia and 2 cubic foot undergoes a process of 90 psia and 0.60 cubic foot, during which the enthalpy increases by 15.5 BTU. C sub V, that is the specific heat at constant volume, is equal to 2.44 BTU per pound mass Rankine. Determine delta A, letter A, delta U, B, the specific heat at constant pressure, and the specific gas constant. Okay, so let's write our given down. So first we have P sub 1 is equal to 15 psia, V sub 1 is equal to 2 cubic feet, and then we have P sub 2 is equal to 90 psia, and V sub 2 is equal to 0.6 cubic feet, okay? During which the enthalpy increases by 15.5. So delta H, which is H sub 2 minus H sub 1, since the enthalpy has increased, therefore 15.5 is positive BTU. Okay, now C sub V, let's write it also, 2.44 BTU per pound mass Rankine. Now, our required is delta U, C sub P, and R. So for delta U, the formulas for delta U is M C sub V delta T. That's a common formula, but we cannot use it right now because we don't have the given temperatures for T2 and T1. So what we need to use as our formula is a formula that I have discussed in the previous video regarding conservation of energy, which is delta H is equal to delta U plus delta WF. Okay, so here delta U will now be equal to delta H minus delta WF. So we can first solve for delta WF, or the change in flow work. So that is equal to P2V2 minus P1V1. So our pressure and volumes are given. So we have P2, 90 pounds per square inch, times V2, 0.6 cubic foot. Okay, this is in cubic foot, this is feet, and this is inches. So we need to apply a conversion factor. 144 square inch is 1 square foot. Okay, so if we examine the units there, square foot cancels out, then square inch also cancels out, and we have pound force feet as our unit. Okay, so pound force feet, we need to convert that to BTU. So 1 BTU is equal to 778 pound force feet. Okay, so pound force cancels out, feet will cancel out, and the final unit here is BTU na. Okay, so we subtract P1V1. So I will not write the units anymore. 15 times 2, and then you multiply 144 and divide by 778. Since 144 and 778 are common factors, we can go ahead and factor those out. 144 over 778. So you have 90 times 0.6 minus 15 times 2. So delta WF, let's get our calculator. So we have 90 times 0.6 minus 15 times 2 is 30. And then let's multiply 144 and divide 778. So we have 4.44 BTU. Okay, so we can now go to this formula on our next page. delta U is equal to delta H minus delta WF. Delta H is equal to 15.5. So we have delta U is equal to delta H minus delta WF, or delta workflow, change in workflow. This is 15.5 BTU minus 4.44. Let's check the given. Okay, 4.44. So we get our calculator and we do 15.5 minus 4.44, and the answer is 11.06 BTU. Let's write that down. 11.06 BTU. So that is one of the answers we are looking for. The next unknown that we will solve is C sub B. Okay, since we have already our delta H, and we can solve for delta H is equal to MC sub B delta T. Okay, MC sub B delta T. So we can solve here for C sub B, but we need again delta T. So where can we get delta T? We can get that from our delta U. Delta U is MC sub V delta T. Therefore, delta T is equal to delta U over MC sub V. Okay. So our delta U is 11.06 BTU. And then, so our mass, we don't have a given mass from the problem, but we have C sub V. So let's go ahead and write M, and then this is 2.44. That's our C sub V, BTU per pound mass Rankine. BTU per pound mass Rankine. So we cannot solve delta T from using that equation, but we go to our delta H, and delta H is equal to MCP delta T. And from here, we have delta T is also equal to delta H over MC sub B. Okay? And here we have delta H is equal to 15.5 BTU, and then M times C sub B. Okay? So if we equate the two equations that we have formulated, we have 11.06 BTU over M times 2.44. Actually, I don't need to write the units because they have the same units. No? Can erase BTU there. Okay. So, and then is equal to delta T. This is also equal to delta T. 15.5 over M C sub P. So what do we notice here? We can cancel out M. Okay? We can cancel out M, and we can now solve for C sub B. So C sub B is simply equal to 15.5 times 2.24. Let me just check. From the previous slide if it's 2.44. Okay, so this is 2.44 times 2.44. Okay, divided by 11.06. Okay, so C sub P will have the unit of 2.44, which is BTU per pound mass Rankine. So let's get our calculator and input that. We have 15.5 times 2.44, then divide by 11.06. The answer is 3.42. 3.42 BTU per pound mass Rankine. So we have delta U, we have C sub P, and then last is R. Okay, since we are given C sub B, C sub V, and we have already solved for C sub P, then the formula that we are going to use for R is simply, it would come from C sub P is equal to C sub V plus R. Okay, so from that, R would now be equal to C sub P minus C sub V. Let me change my pen here. Okay, so R is equal to C sub P is 3.42 BTU per pound mass Rankine, minus C sub V 2.44 BTU per pound mass Rankine. So R is equal to, get our calculator, let us subtract their 2.44. So 0.9795 BTU per pound mass Rankine. Now it would be possible to for the problem, if we would be asked, no, instead of BTU per pound mass Rankine, it would be possible that the problem would ask for a unit in pound force feet per pound mass Rankine, because that is the more common unit for R. So in that case, no, but this is also an accepted answer. Di naman in-specify na sa problem what is the unit, no? So I'm just explaining what you'll do if ever the final unit is in pound force feet per pound mass Rankine. So from that answer, we simply multiply 778 and we will come up with 762.07. Okay? So 762.07. The unit of that is in pound force feet per pound mass Rankine. Okay, let me box that. So, okay, let's go to our problem number 2. Okay, for a certain gas, we have R is equal to 0.277 kilojoule per kilogram Kelvin. And K, so K is the ratio of specific heat and heats, and this is equal to C sub P over C sub V. Okay, so what are the values of C sub P and C sub V? Okay, letter B, what mass of this gas would occupy a volume of 0.425 cubic meters at 517 kilopascals and 26.7 degrees Celsius? And letter C, if 31.55 kilojoules of heat are transferred to this gas at constant volume, so that is very important, constant volume, because it means to say that your Q would be equal to mCV delta T, okay, because it is at constant volume. Okay, what are the resulting temperature and pressure? So let's first solve. Let's go ahead and solve letter A. So a formula that we could use to solve for Cp and Cv given K and R would be C sub V is equal to R over K minus 1, and we can also use C sub P is equal to KR over K minus 1. So it's up to you. No? And then after solving one of those specific heat, you can go ahead and just use this equation. K is equal to C sub P over C sub V. Okay? So let's say I decide to use R over K minus 1. So I have 0.277 kilojoule per kilogram Kelvin divided by K minus 1. So we have 1.384 minus 1. So let's get our calculator. So we have 0.277 divided by 0.384. So the answer is 0.721. 0.721 kilojoule per kilogram Kelvin. Now how about, so let's just go ahead and put a box to that. Now how about C sub P? Okay, so from here we have K is equal to C sub P over C sub V. So therefore C sub P is equal to K times C sub V. So 1.384 times C sub V, which is we have solved that, 721 per kilojoule kilogram. Okay, so let's get our calculator and let's multiply that by 1.384. So we have 0.998998 kilojoule per kilogram Kelvin. Okay, 0.998. So let's box that as well. So we now go to letter B. What mass of this gas would occupy a volume of 0.425 cubic meters? Then we have the given pressure, 517.11 kilopascals and 26.7 degrees Celsius. So what we'll do there, since we're given the volume, pressure, and also the temperature, we could just simply use the perfect gas law. Okay, so for letter B, we simply use PV is equal to MRT, and we are looking for the mass. No? We're looking for the mass. So mass is equal to PV over RT. Okay, so pressure is equal to 517.11 kilopascals. So kilopascals, that is kilonewton per square meter. So let's just go ahead and put times 10 to the positive 3 to make it newtons. Volume is equal to 0.425 cubic meters. And then R is equal to, that is already given, 0.277 kilojoule per kilogram Kelvin. So kilojoule is actually kilonewton. So my bad here, no. We don't need to put times 10 to the negative 3 anymore, because we have kilojoule, and kilojoule is kilonewton meter. So the kilonewton here would also be cancelled out by the kilojoule here, no? And kilojoule is, let's just put this as kilonewton meter. Okay, so kilonewton per kilogram Kelvin, that is my R. And then the temperature is equal to 26.7. So that is not absolute unit. So 26.7, you need to add 273. Okay, so let's just examine so this is in Kelvin. Let's just examine the unit. Okay, the cancellation of units. So let's observe that we have Kelvin would be cancelled out. Kilonewton will also be cancelled out. We have here square meter, and this is cubic meter. So one of the meters would be left, but there's another meter in the denominator, so that would also be cancelled out. So the final unit is simply in kilograms. Okay, so let's go ahead and get our calculators. So what we can do here, because the Windows calculator is a bit confusing. So 26.7 plus 273, we can go ahead and 299.7. I'll just take note here, 299.7. Okay, let's go back to our calculator. And then we'll do 517.11 times 0.425, and then divide that by 2.277 times 299.7. Okay, so the answer is 2.65. So the mass that would occupy the said volume is equal to 2.65 kilograms. So that is for letter B. Okay. So letter C, just check. Letter B, what mass? Okay, so we're already done with that. So letter C, if 31.555 kilojoules of heat are transferred to this gas at constant volume, so this is the formula that we will use there. No? From here, you have Q is equal to mCV delta T. Q is equal to m C sub V delta T, and delta T is T2 minus T1. Okay, your T sub 1 would be 299.7. Okay, and then we will have to solve for T sub 2. Okay, so that is how you'll solve for T sub 2, and then for the pressure, we would have to use the what do you call this? The combined gas law. Okay, so from this equation, first from this equation, let us solve for T sub 2. Okay, mCV T sub 1. So we have mC sub V T sub 2 is equal to Q plus mC sub V T sub 1. And T sub 2 would be Q plus mC sub V T sub 1 over mC sub V. Okay, so T sub 2, so Q is equal to 31.55 kilojoules. Then no need to what did I put? Quantity. Okay, so 31.5 plus mass 2.65 kilograms times C sub V. So let's just go back here. C sub V is equal to 0.721. 721. Okay, let me I need more space. Let's just go to the next page. We have T sub 2. T sub 2 is equal to 31.55 kilojoules plus mCV T sub 1. So M is 2.65. 2.65 kilograms. And then C sub V is 0.721 kilojoule per kilogram Kelvin times T sub 1. T sub 1 is 299.7. 299.7 Kelvin. Okay, and then we divide M times C sub V. So again, mass 2.65 kilograms times C sub V, 721 kilojoule per kilogram Kelvin. So let's check first. Let's check the cancellation of units. Okay, kilogram cancels out from there. Kelvin will cancel out from there. Kelvin kilogram will also cancel out here. So on the numerator, it's kilojoule. Okay, kilojoule. And then on the denominator, we have kilojoule per Kelvin. So kilojoule will cancel out, and the final unit is Kelvin. Okay, so T sub 2 is equal to, let's get our calculators again.
Pwede nyo akong sabayan dito. So, 31.55 plus 2.65 times 0.721 times 299.7. Okay? And then we divide that by 2.65 times 0.721. Okay? And the answer is 316. No? 316.21. 316.21 Kelvin. So let's box that. That is our T sub 2. Now, if ever, no, because in the problem the temperature is in Celsius, if ever that the problem would require you to solve it in Celsius, then you simply need to subtract 273 from there, okay, to make it Celsius. So we won't do that. We will go ahead with the next unknown. So we already have the temperature, and next, what is the pressure? Okay. So for the pressure, we can use P1V1 over T1 is equal to P2V2 over T2. Okay. And pressure, the resulting pressure is pressure sub 2. Pressure sub 2 would simply be P1V1 times T2 over T1 times V sub 2. Okay. So pressure 1 is equal to 517.11 kilopascal. V sub 1 is equal to 0.425 cubic meter. T sub 2, that's what we have solved here, 316.21 Kelvin. By the way, this is kilopascal. And then T sub 1 is equal to 299.7 Kelvin. And V sub 2, let's go back, V sub 2. V sub 2 is equal to this one, 0. From letter B, it says here what mass of this gas would occupy a volume of 0.425 cubic meters. It signifies that the volume is constant already because the gas would occupy this certain volume. So therefore, volume is constant. V1 is equal to V2, so we can go ahead and cancel that out. Cancel Kelvin, and the final unit here is kilopascals. Okay, so we must understand and read the problem for thermodynamics very carefully. So 517.11 times 316.21, then divided by 299.7. So the answer is 545. Let's just round it off to 0.60. So 545.60 kilopascals. Okay. So that's it for our two problems regarding specific heats, enthalpy, and entropy. I hope you learned something. Thank you for watching.